good. So welcome everybody to our first webinar for the year 2024 for the Superfund Columbia University Northern Plains Superfund Research Program. Thank you to all of you who have joined us from many different places, both at Columbia, in the Northern Plains, and elsewhere. For those of you who don't know me, I am Ana Navas from the Department of Environmental Health Sciences at Columbia University. I am the director for the program. And today we have the pleasure to have with us one of our leaders for the center, Benjamin Bostick, Dr. Benjamin Bostick, who is the leader of the Project 5 for the center. He's also co-lead for the Community Engagement Core, and I believe co-lead also for the training component and training and research component. So Ben plays lots of different hats because he has many different skills. And he's also involved in Project 1 and in basically the whole center. He's a very, very important contributor. In terms of his background a little bit, he did his training as a Bachelor of Science at the University of Idaho, and also in his Master in Soil Science. And then his PhD in Stanford in geochemistry, and then a postdoc also at Stanford. Then I believe you were in Dartmouth, if I remember correctly, Ben, and then you came to Columbia, which was great for us. So with this, all yours, we are really excited to hear about your new science in arsenic remediation.
All right, so thank you for the introduction, and I'm going to share my screen. And somehow I didn't start on the first slide. So I'm going to talk a little bit about how we actually try to see Superfund related projects go from a kernel of science into a piece of reality today. Many of us are familiar with water quality issues of different sorts. I'm going to be talking about how we remediate environments that are contaminated with arsenic, in particular groundwater arsenic, using iron-based remediation technologies. I'm going to talk about a couple of different projects today that are sort of detail different aspects of what we've done here at Columbia over the last significant amount of time, I guess, more than 10 years worth of project a little bit. In our first case, I'm going to talk about our current work in looking in Native American communities at water treatment. This is research that, here we are in the picture, sampling in South Dakota earlier this year, or I guess earlier last year now. Time happens. This is research that has involved a lot of people. I'm going to just highlight the names here in red. Adelina Rulea is the graduate student who's really spearheading this effort. Sarah is an undergrad. Jamie's the person in the lab who actually sees stuff happen. Randy and Caden from Missouri Breaks have been involved in the work here in the field, and James Byrne and Sarah Atfield at the University of Bristol have also really helped with this. This is an aspect of water treatment for drinking water. I'm going to also talk a little bit about some of our really recent results that relate to our Superfund projects in the past, where we were looking at magnetite-based remediation. And the reason is, you know, those are things we did, I'll call it, for science, and, you know, with the point of bringing it to the field and actually implementing it in practice, that's proven really challenging. And this is now in sort of a development where in many ways we're on our way to sort of doing this in the field for the first time at a place in Denmark. Again, lots of people to thank. Adelina is the one who's really led our work here as well on this in the lab. Neil Durant from Geosyntec is the consulting firm that we've worked a lot with, and Rasmus Jacobsen and Torben Jørgensen sort of leading the project overall. This is project originally, funded, all aspects of this have really been supported through our Superfund projects at NIEHS. It also is supported partly by the Department of Energy for understanding ways of treating water that are more energy efficient, as well as, like I say, our more recent work applying those Superfund related projects to a potential site for actual remediation supported through Geosyntech and COE. As Anna mentioned, I'm from Idaho, and I think it's useful to sort of step back in time to one of the reasons I became an environmental scientist. This is the Bunker Hill Superfund site, not so far from where I grew up. It is one of the largest Superfund sites in America, and it's a place where they have historically mined really large amounts of silver and lead, among other things. And rather than, deal with those piles of tailings, they dumped them in a river and sent them downstream. And so a big part of this area's contamination is a really wide distribution of contaminants. And down the street from my dad's house is this sign. The sign sort of sets up some of the challenges and approaches what I'm going to talk about today. First of all, it does another thing in addition. It says, in addition to pointing out that water and soil are places where the contamination resides, it also, brings it home. This is, the problem with environmental contamination. It really affects you. It affects your family. In this case, it might have affected me. Maybe it explains a lot. But certainly these are things that happen in real communities, and it's really important to understand that. This is a picture of what that community looks like, not downstream, but still in an area that is impacted, about 50 miles away. Again, pictures to just bring that environment home. The soil contamination is pretty ubiquitous from, in this case, very far from the source of contamination originally, and it affects the water. You can if we think about dual approaches, this would be great to deal with, but in general, water is mobile. It things that when you ingest, you get all of, and most of the things that are in it, that are toxic are bioavailable. In contrast, the sediment, you may go touch the sediment here on the surface, but in actuality, we don't always necessarily interact with them in the same ways. We can cover them up, and often a big portion of the metals in them are not bioavailable. In fact, that's a big advantage. If we can convert something from the water into an unavailable form in the solid, we've remediated it in many cases. So that's going to be a goal of remediation. As we sort of think about what we want to do, I think it's really important to state how some of these goals affect how we end up doing things and translating science into action. On one hand, the goal of cleaning water is obvious, clean water, right? It's a lot less obvious how clean. And, I'll throw out a couple examples. Let's say we want to, meet a water quality guideline. It's not always enough. It's the same water body here. Generally, my goal for how clean is clean enough for my family, right? Like I want this water to be, and it should be our goal in science. We're trying to make not just a remediation technology that meets the legal requirements, but we want to make something that's actually going to be something I can recommend for people I care about. That's a challenge. Not only is it hard to do that once, it's hard to do that for the long term. And remediation removing something once, in this case, treating water and having it go down, only counts if you can do it for long enough for things, for you to count on them. That's a problem when conditions can change, or if there's a broad, diverse set of conditions that are present. So how well something works and how long it works actually are really big issues that we often don't work with very well in the science that actually impact how we actually use data today. So with that in mind, I'm going to sort of present our information now and explain sort of the context of why we do certain experiments. Hopefully that makes some sense. I'm going to focus on how iron is a central component for remediation efforts. This is a picture from Grand Prismatic Springs in Yellowstone. I used to teach field geology, so it's a good spot to teach this. Hot springs comes out of the ground. Iron oxides form as the system cools and interacts with air, and it scavenges trace metals out of that water. So in this case, arsenate, or arsenite in this case would also do pretty well, sticks to those metals or sticks to those iron oxides and largely keeps it out of the liquid, so that much of the arsenic-rich hot springs in Yellowstone are not arsenic-rich by the time they end up in rivers downstream. Okay, not all iron oxides are the same. You can see there's multiple colors of here in this picture. There's different kinds of iron oxides. They have different reactivities. And in fact, if we want to think about why arsenic is a prevalent contaminant, it really relates to the fact that some of the chemical forms of iron oxides, although they form and can scavenge stuff, are also prone to reduction. So over the course of, if I was to, summarize the last 25 years of environmental science work related to arsenic, it is when those iron oxides are reduced chemically by biological systems like iron reducing bacteria or an abiotic system, that arsenic and that iron can dissolve and end up in solution. So that's how we end up with a ubiquitous groundwater problem. But if we can, push it the other way and have iron oxides form, we actually can be in an environment where we can treat water. And so this is just an example of a wellhead where it's doing it naturally, where there's a lot of iron in the water. That iron can precipitate, and in doing so, it would scavenge the arsenic out and actually have a remediated water supply. Unfortunately, you don't often drink it after that occurred. You don't necessarily wait. So it is an issue. So how does this come into what we're doing now with our current water systems? Well, in a couple of ways. So our Superfund projects today are dedicated to trying to address arsenic contamination, in particular across the United States. That's a widespread contamination issue. This is just a map of arsenic contamination distributed across the US, as sort of a probability map. Anything that's even the lighter shade of green means at least 10% of the wells in those regions have arsenic concentrations in excess of safe drinking water limits. So the main point in this map is there's a sizable fraction of America where a lot of water is contaminated. In some areas, more than half of wells, but certainly in nearly half of America, it's more than 10%. Right? Why does that matter? Well, if we want to think about a remediation technology, we want one that's going to work, hopefully, over a range of arsenic concentrations, but also work over a range of environmental conditions. Each of these areas, have very different kinds of water compositions, everything like that. There's lots of different problems we need to try to address. So it turns out it's not quite as simple either, in that almost never is there only one contaminant. I mean, often, I guess I shouldn't say almost never, but it isn't necessarily that there's only one contaminant to worry about. Arsenic is certainly abundant and common, so it's often the only contaminant, I guess. But in many cases, for example, here in this, tribal community in the United States, we have, arsenic and uranium often occurring together. This map shows red dots, blue dots, black dots, and white dots. The white dots are safe according to the maximum contaminant level for both arsenic and uranium. The red ones exceed it in both. The blue exceed it for arsenic, and the black exceed it for uranium. Main point here, many places do not, have unsafe water. And in this case, it's nearly half. And of those, a certain fraction have arsenic as well as uranium, or uranium instead of arsenic. So ideally, if we have a water treatment system, we'd like it to work for both. you can see just how many, when we start looking at scatter plots of data here, just to give you an idea. If we want to think about how many wells or how many samples we would have above an MCL, we get certainly a fraction. If we look at the uranium above the MCL, we have a different fraction. And then just as an editorial comment, if we have a more realistic level for uranium that we might hope for, then rather than 30 micrograms per liter, if we put it at 10, we actually have quite a bit of a plot like this showing just how ubiquitous some of the exceedances might be. So again, if we're thinking about water treatment, we would like to have a water treatment system that would work for both arsenic and uranium. But either one would be useful in isolation, but then you'd really want to know where you were using it to make it most useful. So there are a lot of water treatment systems. If you Google this, you get, some, wherever you go, there are lots of companies pushing up their, website. There'll be lots and lots of things that pop up about, systems that are available. If you look at city or county or state level departments of environmental quality, they will also present many alternatives, sites that could, places that you could use for water filters in those different locations. What I would argue though is the existing technologies are not nearly as good as we'd hope they would be. These are just a set of data from the literature showing some of the difficulties in making that work. On one hand, we have the top condition here, and here where the condition of an iron oxide medium is just not favorable for the filter to be very effective. So water coming through a water filter isn't actually working. In the bottom case here, we see older filters don't work well, and unfortunately a new filter, as you progress through months, even just a few months, it eventually in many cases can exceed in drinking water quality. Or a reverse osmosis system over here on the right, where some of them appear to work well, randomly spot checked, and others don't work at all. So why does that matter? Well, there's a lot of reasons they're failing, right? Or some of them fail. There's a lot of complexities in water chemistry. Some filters only work under certain conditions. Many of these filters, even when they do work, are only working for one contaminant. A big part of it is the media has a finite lifetime. It runs out. And even worse, and sort of from a public health, I'll call it disaster point of view, in most of these represent cases where somebody's actually made measurements. But the vast majority of times, we don't actually know if a water filter is working, and we either assume it is or we don't use it because we assume it's not, either of which is not a very good outcome. So we really don't have a good way of understanding what those results mean or how to use them. Both arsenic and uranium are really common. If there's one thing that we have learned in our studies of integrating data across the United States, this is two studies from our Superfund group. On the left, arsenic in public water supplies, and on the right, uranium in public water supplies. Both of those results say it turns out inefficient treatment or no treatment at all in some cases is what they're hoping for in community water systems is still generating conditions that are hot or have output water concentrations that are higher than they should be. So this is not, on one hand, you'd say, oh, these are problems associated with private wells, but a public well system where people who they're theoretically running them that know how to run them and monitoring them, we still end up with some of these issues. So we really need public, water systems and private water systems that have a treatment methodology that are dependable. And this is where our sort of research comes in. So all that was a rather long introduction. But the reason it's long is I want to sort of give us that foothold that then explains why we're doing the things we do. In this case, our primary approach is looking at phototrophic reactions. We're looking at actually photosynthetic bacteria in this case that oxidize iron in solution. In doing so, they generate it's a more controlled process than just oxidizing iron with oxygen, and it actually generates media that are potentially very effective for retention. I mean, you can do this even in a system that has no oxygen, so it's not something that we have to do. Why do we do that? Well, there's a couple advantages of doing it. One, iron oxides can retain metals. This is on the left is a adsorption, isotherm that relates how much dissolved metal on the x-axis and how much solid phase metal is on the y-axis. So something like arsenate, you can see that has a steep curve that then flattens out. What that really means is if we put arsenic into a system, almost all of it goes onto the solids initially. And we get strong retention in the solids and we maintain a low solution phase composition. Eventually, you exceed the MCL, in this case, the red line, and that would mean, oh, that media is no longer able to retain any more at a significant concentration. So at that point, that would be the lifetime of media. Okay, for arsenic, because that's a very steep curve, we can actually treat a lot of water before that happens. Arsenite adsorbs less well, at least in a modeled sense here. And what you can see here is because that curve is flatter, arsenite, even we don't need nearly as much on the solid phase before it's no longer effective. And down here at the bottom, one of the problems with uranium just doesn't stick to stuff. That's one reason that uranium is a relatively common environmental contaminant where the solution composition is carbonate rich and has the right chemistry so that it doesn't really get retained strongly on solids. Okay, so what does this set up? This sets up a couple of observations, right? This kind of curve says, first of all, adsorption for different chemical forms of things is not the same, and it's finite for all of them. So if we want things to work better, we need to do two things. One, we would like to convert the chemical forms of arsenic, for example, from 3 to 5, or uranium from uranium-6 to uranium-4, which then would shift these lines up and mean we get much more effective treatment. The next thing is, because adsorption is finite, these are curves, what we really want to do is also have a way of regenerating our media and recycling it to enhance our system. So our research follows both of these paths to try to look at how that occurs. And our idea to do that is to build basically what we call, by we, I mean, the science literature has developed into calling a biogeobattery. It's an iron-based battery that uses microbial oxidation using photosynthesis and microbial reduction using dissimilatory iron reducers to cycle iron. And in doing so, we can treat water and regenerate media. Okay, so that's basically what we're trying to do. And it turns out that cycling also has some additional benefits which relate not only to the long-term treatment, but also to modifying arsenic and uranium. Well, with that in mind, we've made a fair number of these kinds of systems over time in various levels of complexity. This is a sort of a nice picture of Adelina's current setup in the lab. In reality, it looks a little bit like that. Actually, compared to my drawings do never look like reality. So I'm very impressed with her drawing here in that sense. And basically is a reactor here where there's groundwater flowing in. It has a window because we have to allow light to interact with it. That light produces iron oxides, which then precipitate in here and would remove the metals from the inflow water, groundwater, and have treated water that comes out the top, basically. So what do we need to do to show that works? Well, the first thing it needs to do is it has to produce the media. One thing we're trying to do here we're not packing a water treatment media that we bought into a tube and we know it's there and it's in a high concentration and we're going to watch it work until it doesn't anymore. We're actually trying to create that medium from groundwater materials. So in this case, using iron from the reactor, if it's present in the groundwater, we may not even need to add any at all to do this. And what we can see is once the system gets established and microbes start to, become active, iron removal is very, very sharp. The bromide curve there just shows that we're getting a certain kind of mixing in the system, that it's the bromide and the iron started out parallel to each other. What's great about a system like this is it also works when we speed it up. you can imagine a water treatment system that had to go really slow for a biological process to happen. You're sitting there waiting for the microbes to produce an iron oxide to absorb arsenic, so you can only pump water in really slowly, would not be a great system. What we can say is if we actually increase the rates of flow through this system, we're still able to create the medium fast enough and actually also to treat the arsenic, is what I'll show you in the next slide. So how does treatment work? Well, in the case of real sort of chemical compositions like we would find in our communities, we end up, which are challenging in the sense that the concentrations are low. So we need, on one hand, we don't need quite as extensive a percentage of removal to get to safe. On the other hand, it's challenging to get to safer levels when you start out low because everything happens more slowly. So what do we have here? Well, we have phosphorus removal around 80%, arsenic removal of 65%, but both of those meeting sort of stable levels. Uranium removal is incomplete and really is something we need to work on more, but actually at the same time, because uranium removal is mostly possible due to reduction, it indicates that there's actually some chemical conditions changing. In terms of arsenic in these reactors, one nice thing that we can observe, because these are systems that are iron cycling, they actually poise the redox conditions in a useful place in terms of redox and pH space, where arsenic can be oxidized. This is X-ray spectra from the synchrotron showing some of that happening. And we also have some evidence that the same process is happening with uranium, although we don't have the same speciation data yet to verify that. But the point is, what we do have evidence for is that this biogeobattery, because of its redox cycling, is able to cycle iron and uranium in a way that should enhance its utility. The next thing in thinking about what we're doing now is how do we improve a reactor like this? Well, to do that, I'm going to show you a little movie of what it looks like when you have water flowing through it. Well, you can hopefully see there on your Zoom screen, some darker shading in there as it's sort of moving through a front. That's actually a front of the iron precipitate forming. And you can see that sort of channeling through. What's important about that is it shows you visually what we can model here pretty well. And that is in that reactor, we have flow occurring in certain areas, but not in others. So there's lots of places that the flow doesn't stick, and that makes treatment actually less effective. It does make the reactor bigger, which is nice because then you can theoretically have better flow rates, but if it doesn't work well, it doesn't matter. So one of the things we're doing is creating newer reactor designs that are essentially large series, reactors, all of which are designed in a way that we minimize dead space to make the engineering work better. And hopefully those kinds of reactors will also work better, right? So what we have sort of at this stage right now is promising in the sense that we can make iron media really, really pretty quickly with this approach. That iron media does actually retain our arsenate and phosphate quite well. It actually also retains arsenite well enough to do what we need to do, and is appearing to affect the uranium oxidation state faster than a lot of traditional catalysts. So it still might be useful for arsenic and uranium removal as well. Again, with further improvements, that's one of those things you want to keep going and make sure that we can do that. How we want to do these things, how the field improvements we want to make in the lab translate to the field, which is a key thing, is also really key. I think one of the things we're moving towards and we're close to is implementing these in a field environment where we can actually see them actually working under the most realistic conditions, where we're actually using the same input water and the same microbial communities and all the other things that are necessary for this to be fully translatable and to be able to understand how they work and their lifetimes in those environments. So with that, I'll sort of transition here to the second part, which is magnetite-based remediation. We're trying to do this at the Colstrip site. So just a tiny sliver of information for those of you who don't know where that is, which is pretty much everybody. Colstrip is a place in Denmark. It's on the island of Sjælland, near to Copenhagen. If we sort of zoom in on Copenhagen, it's northwest of the main city of Copenhagen, and I'll call it a bedroom community or a suburb hillet area. Okay, it's an area that has a lot of natural areas around it. It has a lake. There aren't very many lakes in this area, and a lot of protected areas. And like most contaminated sites, is close to people and all those other issues too. So it really threatens not only human populations, but a large number of ecosystems around. Sort of a map of where it works. Just to show you, rather than a map, show you a picture. This is the Kolstrup site. They used to make pressure treated lumber there. That's what pressure treated lumber looks like. For those of you who don't know, that involves copper, chromium, and arsenic. They were all used in pretty high concentrations. And arsenic is the big problem, because usually of those elements, arsenic is more soluble than the others. How much? Well, this is sort of the most contaminated place in Denmark. Maybe I shouldn't overstate that. That's probably a fair statement. It's certainly one of the very, very most. 100,000 kilograms of arsenic is on this piece of land. It turns out, in like many places where arsenic was used to do this, they bought soluble arsenic compounds and they put them in piles on the ground. And of course, that ends up somewhere else pretty quickly. So that's distributed over the land surface. It's a lot of doses if you want to think about how much equivalents there are that are dangerous. And in general, this fairly extensive area has, concentrations up to a couple thousand milligrams per kilogram arsenic, and high chromium and copper everywhere too. So given that background, and unfortunately, because it's soluble in very, very shallow soils, and it's close to those water bodies that you see just to the north, that arsenic is on the move. And so this is a place that Denmark is very interested in trying to remediate. So with that in mind, how do we try to fix a site like this? First of all, how do we even, if we want to do a laboratory study to see if it works, well, how do we even decide where to go? Because on a site this big, it's not all the same. And so we've chosen a sort of typical site, not the highly contaminated environments, but actually sort of the more abundant, more common environments where concentrations of arsenic are only, 300 milligrams per kilogram, which is still pretty high. And the concentrations of arsenic in pore water is typically 300 to 1,000 parts per billion. So these are more conventional contaminated areas within that site. And we've been working on these materials now for the last year or two to try to really characterize how remediation might work. And we're trying to do something a bit more targeted than just iron oxides. So we're trying to induce microbial magnetite formation in this case. So this is an idea that I worked on a lot in our old Superfund program with Jing Sun as a graduate student who really did a lot of that work. Why? Well, magnetite, if we can get it to form, is really good at scavenging trace metals, especially arsenic, chromium, and does okay with chromium and copper as well, actually. And it does so in a way that's really useful. Magnetite's also kind of useful because the conditions under which magnetite are stable are different than a lot of those other iron oxides. So you could imagine ferrihydrite, that phase that we were producing in the hot spring, and which is really common in soils and sediments everywhere. This is stable here in this green area. And if you look at where common Superfund sites are, they're normally stable. The water chemistry is not in that environment where ferrihydrite is stable. So what's happening, these systems here, these are just some random, some common Superfund sites that there's data available for. You can see that they fall in this range down here below the ferrihydrite stability, where ferrihydrite is being dissolved and producing iron 2, just like I talked about. Magnetite, so here's the iron 2 stability field for that. Magnetite, in contrast, is stable over a bigger range. So why does that matter? Well, it means that under the conditions that groundwaters have at these Superfund sites, and very likely many others, it's not going to dissolve at all. It's not a vessel that is prone to dissolution and iron 2 and arsenic release. So it represents a much more stable product and desirable product to form. Since our goal is not just, making something that removes arsenic but keeps the arsenic out of solution over the long term, that's something really important to think about. The next thing is it not only removes it and is stable, but it actually puts the arsenic into its crystal structure internally, which means that you can't even wash it off the outside like you could scrape off the sprinkles on a donut. You have to really break it apart to actually get it to release that arsenic. So it's really makes it a very stable structure, very much protected and not dangerous to the environment in the same way as other forms of arsenic. So how do we get that to form? Well, if we just oxidize iron with oxygen, we're going to get a lot of iron oxides, but none of them will be magnetite. So what we have found is this pathway to getting iron oxides to form abundantly, really using oxidizing bacteria, and not necessarily the oxidizing bacteria that are photosynthetic like we used for our water treatment system, because photosynthesis is not likely to happen underground where the contamination is, but using an iron oxidizing species that can work with nitrate or other electron acceptors that basically couple iron oxidation to nitrate reduction so that we can actually have that magnetite produced. We've been studying that, like I say, through our old Superfund program quite a bit and have a really good understanding of how that works molecularly so that we can really tailor conditions so that we are able to create magnetite with a reasonably high yield over time. And I'm going to present the data about how we make magnetite using these microbial approaches. It turns out because it goes through different intermediates and involves iron 2 and green rust as intermediates, we can certainly also try to make those directly. We've tried many of these approaches. One of the things to think about when we're going to actually remediate a site is depending on only one approach probably is never going to be a very likely success story. So we've really worked on multiple components, and I'm just going to show you the data from this microbially produced magnetite part. Well, so what am I going to show you? I'm actually going to show you columns, sort of the most recent results from columns. And it's columns where water that's contaminated or uncontaminated flows through these columns that contain the soil that have that arsenic contamination and where we can hopefully precipitate metals. Why? Well, these are open systems that looks a lot more like the environment than a closed bottle or a closed system, which is how many people start these kinds of remediation tests. So what we're going to start with is different amounts. We're going to start with columns that have sand and soil mixed at different levels so that we get some idea about a range of how much contamination might be present in soil. And we are going to, have duplicates to prove we can get reproducibility, et cetera. All those things turn into very quickly involving thousands of samples coming out of one of these. And we're going to flow water through it over time, right? So that allows us to look, because we can have control flow rate and we have a reasonably small system, we can simulate reasonably long-term processes using these kinds of approaches and do so in that open system where it's most relevant. These are columns when we actually look at it, each one is for each of the columns, but the left is before anything happened, sort of after equilibrating, and then the right is after we started to add the iron solutions. And when you start looking at them, you say, they don't really look too different. I'll zoom in on a couple that make it more obvious. But you're right. We see some modest changes in the colors. For example, you can see here there's an orangey layer here at the inlet, and at the top layer at the outlet that things are turning more black relative to what it looked like in the beginning. So we can see changes in mineralization that are occurring, and we're still sort of quantifying those changes in terms of how much magnetite, for example, is produced. What we can see, though, is that when we do those things, the concentration of water that comes through the column, the arsenic is decreasing significantly over time. So these are concentrations of arsenic. You can see that in the more dilute samples, by the time we get to 5 pore volumes flushing through the system with iron 2 and nitrate added, we've basically eliminated the arsenic from effluent. We've treated it very effectively. And in fact, in all of these systems here, even the ones that have, hundreds of ppm arsenic in the solid phase, which could theoretically generate a ppm or nearly 1,000 ppb of arsenic forever for essentially a very long time, they don't really do that. So we see effective remediation. And that remediation is tied to when iron is breaking through, which interestingly is also when, under a typical system, when reducing conditions happen, when arsenic is actually mobilized. So we see the opposite trend. Okay, we can actually look at all the chemistry changing and really identify the chemical processes in this case, sequential reduction. We see manganese coming out before iron. With these kinds of data, we learn a lot about the chemical processes and biological processes that are happening that are really useful to us. But in terms of what we're, the bottom line, this is sort of the figure where we look at the very long-term treatment. So elapsed pore volumes on the x-axis, so time. And if you think about groundwater flowing a certain rate over, then 300 pore volumes represents hundreds of years of time. And we have a remediation step here, this S2, when we had everything get lowered except for the control. And then we created a system that was anaerobic when things should get as horrible as they could get. They didn't get anywhere near to as horrible as they were in the beginning before treatment. So we have some reasonable results. And then long-term removal of about 90 or 95% of the arsenic was maintained. Copper and chromium didn't do anything. None of these treatments made them bigger or smaller, essentially. They were not a big part of that. I still want to put them in there because they're still, again, contaminants of concern, and there are a few things happening. So what do we find? Well, magnetite, this is a field site that is, really needs a remediation plan. And this appears to be a very promising approach to actually do it. We get magnetite to form, and it certainly appears to scavenge the arsenic very effectively. It appears to be long-term stabilized. It could be more effective. We could have had a higher proportion in that longer-term part of the experiment retained in the solid phase. We probably need to increase the amount of iron mineralization we do to make that happen. Ultimately, we need a field test for this. And one of the things I think is fascinating about this, all these stringent limitations, like needing long-term stabilized technologies, ones that might work if there's climate change and long-term changes in the system that we certainly know could happen. On one hand, those represent really big challenges for us in science, but on the other hand, they also are a huge opportunity. They are the things that drive us to be able to try to use these technologies and actually really explain why developing a new technology is worthwhile, because a lot of other technologies might not satisfy that. That's the end of what I want to talk about with science. I just want to end on a couple notes here again about how do we, it's easy to say you want to develop a remediation technology and try to use it, but I want to really emphasize an aspect of our work at Superfund that I think is really important. How do we actually get projects like this going and actually try to do them and make them useful to people? I'm going to close on a couple things I think are really important to realize. This is a picture of all of our research team and our external advisory group in the Badlands in South Dakota. A piece of lesson here, if you want to work in communities and understand what affects them and how to interact with them, you got to be there. And not just be there on vacation. Badlands are a great spot to go if you wanted to do that, but be there in community events, be involved with the community, let them help shape the science as well, and shape the kinds of systems that we think we need, help them, inform the kinds of technologies that would be useful or problematic, and really work with them to make this technology something that is theirs in the end. And last but not least, all that stuff takes time. I took this picture, I think about 10 years ago, and our Superfund program has been funded for a couple years, but it takes a long time to go from starting to work on a project to collecting some preliminary data that says it's not crazy, to getting it funded, takes a lot of money to get to that stage as well. And it's going to take a lot more time for this to be a technology that's usable. At the same time, we really want it to happen quickly because these are communities that are impacted by it now. So that's a challenge to do. And again, being there is part of it. So this is some of our, research team working in the field, some, dogs of South Dakota, to leave you here, and I'll take some questions at that point.
Wonderful. Thank you so much for all the hard work, the hard thinking, and your engagement. So let's start with questions and comments for Ben. Anybody would like to start?
I'll just start with a comment while other people get their questions organized in their head. But that site in Denmark, I mean, that's really impressive. The Vineland site, which is the site we worked on, and Ben knows the Vineland site, prior to our current Superfund center, was about 20 times less arsenic in the ground compared to that Copenhagen site. And that was considered the largest arsenic Superfund site in the US. Yeah. So that is a massive site.
Yeah, and it really is a stress test for the method as well, because when there's that much arsenic in the solid phase, that's actually relatively easy to get out because it's not bound in those internal forms like we might be able to produce with magnetite. It turns out it isn't enough to just remediate this aqueous phase. You really have to convert everything in the solid phase and in the aqueous phase to more stable forms for it to not be released over time. So you need a significant excess of mineralization. So yeah, which leads to other complexities in how to do the experiments, it turns out.
Ben, there's a question in the chat for you.
Yeah.
Rob Root, did you find any flow restrictions with the magnetite production in the column experiments?
So the answer is no. We have looked, we have tried in other cases to measure it more carefully with pressure transducers and things. We never actually found a significant amount of flow. In the end, although we added a fair amount of added a fair amount of iron to get that much iron to precipitate to be able to remediate, for example, in this work in Denmark, it turns out that we only added about 1,000 milligrams per kilogram iron to the sample. So the porosity changes by less than 0.1%. And we did not find any evidence that could still matter, but in our our basic constrictions is it doesn't. We don't see a change in the solute, conservative tracer solute transport in the system, and we are able to keep flow working pretty well. I am working with Rasmus Jakobsen, who's really one of the leaders in this on that project, who's also great at those modeling questions. So he will have a much more quantitative answer for that once we can finish developing quantitative models. But certainly something we are thinking about. We also, in other columns, have even done geophysical testing to try to look at how we can spatially resolve where magnetite formation occurs. Other questions?
I wanted also to invite anybody who came to the talk, and maybe you don't come often to our webinars, to encourage you to come in the future. We have all kinds of different talks that we try to make them relevant, especially to Northern Plain communities, but also to other communities affected by hazardous metals. And feel free to come on camera if you would like, ask a question, tell us who you are and why are you interested in this topic. So please feel free. We have 9 minutes left. So you can feel free to raise your hand and share with us anything you would like. But meanwhile, I am going to ask a question myself also to Ben.
Yeah.
And is that it seems that uranium is so complicated. When we think how complicated arsenic is, it seems that actually arsenic is pretty easy, and that you are able to make quite a bit of progress in, at least looks optimistic. But uranium looks much harder.
So-
And is there any hope there?
I think so. The answer, I think, is yes. But you're right. Uranium is a big challenge. So if you think about what community systems do when they encounter high uranium water, it's very often treated by mixing, which to me, I'm not an engineer, so I can say this without getting myself only by making engineers angry, probably. But is mixing clean water with that less clean water so that it meets the MCL. But that's not a particularly satisfying solution. And it's pretty, or indeed just turning off. If we think of the communities in which we work, when they find a well for community use that has high uranium in it, their solution is to not use it. So it turns into a very expensive thing if you just keep drilling or don't have any other supplies. But very much true. Uranium is a challenge to remediate because the places where it's present as a carbonate complex, often with calcium, depending on the calcium activity. And that matters because if it's neutral, it turns out it's not treated by reverse osmosis as well. So you can have systems that are designed to work for things that under some conditions might work, but other solutions don't work as well. So all those things start to, play a role. But the key is being able to reduce uranium, because if you have a system where the redox state of uranium can be perturbed, then it'll end up being a solid and very strongly retained in the solids.
Mm-hmm.
So.
And Ben, Cynthia Clevens is offering field trials in New Hampshire.
I would love to.
Yeah,
I will take you up on it, I'm sure. It's a reasonably simple system. I mean, one of the reasons we like this design is we're having photosynthetic bacteria do a lot of our work for us. It actually can remove other contaminants like phosphate. It naturally is a nitrate remover. So there are some potentially, beneficial things that allow it to be reasonably low maintenance especially if we can make it, the recycling part, which I haven't talked about at all today. But yeah, the idea would be it's a reasonably simple thing to try on a well. But I appreciate that very much.
Yeah, and Cynthia and Tim Chilsky, if you want to say hello or tell us, share with something, or you want to tell us, Cynthia, where you are, or Tim, please go ahead.
Hi, everybody. Thank you so much for making this public. I'm new to Twitter. I'm trained in environmental health, and I've been doing a variety of different things in epidemiology writ large. But I think so much of my time is spent on figuring out exactly how much harm there is, that when I see a talk that offers remediation potential for things that have been in the back of my head for so long, I had to spend some time this afternoon, and I just wanted to see what you had to say, but also just to see how the group talked about it. So hopefully, I've been thinking mostly about East Palestine stuff lately, because I'm in Ohio at Case Western. But thank you very much.
Well, I think remediation is a really important thing to look at. At the same time, if we can find clean water, it's even better. And so one of our other projects that I also work on that I really think is important is improve the understanding of where contamination resides underground so that we can tap clean water sources rather than the dirty ones, especially in these kinds of contamination issues, which so often are affected by natural contamination, right? So it's not like getting further away from a contamination source necessarily helps you in the same way. So
thank
you. Yeah, thank you for joining.
Yeah,
and very welcome. Feel free to join anytime.
Wow, thank you.
And anyone who has any questions or comments, I'm happy to hear, or like I said,
I have a quick
you bet.
I have a quick question then.
Yeah.
So I mean, maybe one of the issues with uranium is that iron-3 is an oxidant of uranium-4, so it can oxidize uranium and make it soluble. So maybe that's an added challenge. So I wanted to hear your thoughts about it.
So there's two different things there. Yes, it depends as it turns out, the pH breakthrough where that really occurs is also close to neutral. So there is, some potential under certain pH conditions where things. We try to have both, right? Like one of the things about a biogeo battery that's iron cycling is you end up with both iron-2 and iron-3 present. So you're not necessarily just in the stability field of where iron-3 can do it. The other aspect I think is really important is iron-3 is usually for most intensive purposes insoluble, right? And so when you have uranium-4 and iron-3, two insoluble solids, they can persist pretty often together because it turns out it's really hard for them to chemically react when they're two of the less soluble things on the periodic table. So you have the good news is, on for some senses that there's a metastable possibility where you can have iron-3 materials and uranium-4 present. But you're right, there's lots of things to consider here all along the way.
Wonderful. So it sounds amazing science to continue and discussions and work to do, hard work. We need to be patient, but it's great to see the progress being made. So congratulations, Ben, and the team, Adelina, and everybody else for the great work. Thank you so much, everybody, for joining. We'll be together again in a month from now. Also, it's going to be a different topic. And as we are a very interdisciplinary center, so we'll be talking about molecular pathways and the impact that these hazardous metals have on health outcomes and the pathways involved. So please join us in a month. Thank you so much and see you soon. Bye. And thank you, team, for joining and everybody else new.